Good afternoon, dear friends. I welcome you back to today's session on GATE online coaching being conducted by Jawaharlal Nehru Technological University, Anantapur, Kakinada and Yogi Vemana University, Kadapa. I hope you had a very good rest yesterday night and you are fresh for today's class. Today we are going to discuss about theories of failure. We are going to discuss about the theories of failure. But before actually going to discuss about theories of failure, we will first clarify the doubts, some of the doubts raised by some students from the previous class. The doubts we will go to today's class. So first, premnathreddy@gmail.com. Could you please explain how to convert shear force diagram to loading diagram and bending moment diagram to shear force diagram? Premnath Reddy, I have discussed about this in my video. So please go through that. So it is simply by following the concept df by dx is equal to rate of loading W. Okay. First derivative of the shear force is equal to rate of loading and the first derivative of bending moment is equal to shear force. So dm by dx is equal to shear force F. So following this concept, you can draw the load intensity diagram from shear force diagram and also from bending moment diagram we can draw the. Thank you very much. Please continue to follow our lectures. mtraju9670@gmail.com. While you teaching, it is buffering, sir. So it is your local problem, Mr. Raju. It is your local problem. You must be having issues with the connectivity. So please take care of your connectivity. Our side, the connectivity is good and the lecture is continuously coming. Bandwidth for some of the students attending from their mobiles or in areas where the connectivity is poor. So from our side, there is no connectivity problem. We are having good bandwidth and our lecture is coming continuously. So that may be a local issue, please. praveenkumar@gmail.com. Very useful, great lecture, sir. Thank you. So thank you, Praveen Kumar, for your good words. I am repeating yesterday's questions again, sir. Due to technical error, the answer to my question had skipped in the video or not recorded. Is shear force diagram and shear stress diagrams are same? Is it enough for GATE by following the lectures and PPTs with practice? First of all, the first question, is shear force diagram and shear stress diagrams are same? No, it is not same. Praveen Kumar, I would like to repeatedly say that shear force diagram represents the variation of the shear force along the length of the beam. We are drawing the variation of the shear force along the length of the beam, that is called the shear force diagram. Whereas the shear stress diagram is the distribution of shear stress or variation of shear stress across the depth of the beam. So shear force diagram is along the length of the beam, shear stress diagram is along the depth of the beam. So don't get confused between these two. I hope this is clear now for you. Is it enough to prepare for GATE by following the lectures and PPTs? Yeah, for fine. As far as my topic is concerned, I think I have covered all the syllabus. I am covering all the syllabus which you can work out by yourself. The explanation for the problem along with the solution is also given. So if you solve those problems, this may be more than sufficient. But you have to be careful because whatever I am dealing is with respect to GATE 2020 syllabus. So GATE 2021 syllabus is not yet available. So once 2021 syllabus is there, you have to just look at if any new topics are added. Accordingly, you have to modify your preparation. If necessary, we will come back with online classes once the GATE syllabus is concerned, and whatever deficiencies are there between 2020 syllabus and 21 syllabus, we will try to cover at that time. Sambashiva Reddy Saniko Barla. Sir, moving of wheel JCB is UDL or not? I explained to you yesterday also, Mr. Samshivareddy, JCB, the entire load is transferred to the road surface or earth surface through the wheel load. We generally consider the wheel load as a point load. So it is a moving point load. When the JCB moves, it is a moving point load. It is not a uniformly distributed load. Mansoori since 2000. Sir, at neutral axis, no extension occurs. And also modulus of rigidity is constant throughout the member. Then shear stress is directly proportional to shear strain. At neutral axis, shear stress is maximum. Then what about shear strain? Mansoor, at neutral axis, there is no extension or compression. The strain at neutral axis is 0 due to bending moment. Extension of layers, whereas neutral axis, there is no extension, there is no contraction, or the strain, the bending strain at neutral axis is equal to 0. The bending strain at neutral axis is equal to 0. Then regarding shear stress, the shear stress is maximum at neutral axis for rectangular or circular sections. For certain sections, it may not be maximum at neutral axis. So the shear stress is not 0 at the neutral axis. Okay, the shear stress is not 0 at the neutral axis. Shear stress is directly proportional to shear strain, modulus of rigidity. Shear strain is defined as. We did not find the day 2 video and PPT from the site, sir. This is N16063. So first 4 days, 3 videos are there. For first 4, 1700108 Sir, for easy calculation of effective stresses, we are knowing principal planes. The calculation of effective stresses is not easy due to inclined loads. Is this the reason why we are finding principal planes, or is there any reason? See, Mr. Sheikh, we are trying to find out the principal planes and principal stresses for structural design purposes. We need to find out where the stress is becoming maximum, where the stress is becoming minimum. So the major principal stress is the maximum normal stress. Similarly, we also find out the plane on which the maximum shear stress acts. So the plane on which the maximum shear stress acts is at 45 degrees to the major principal plane. So by knowing the planes where maximum normal stress is coming and maximum shear stress is coming, it will helpful for us for the structural design purposes. That is why we are calculating the principal planes and principal stresses. muralivenkat@gmail.com. Sir, please briefly explain principal stress in Mohr circle. I think I have explained this yesterday. The Mohr circle, drawing the Mohr circle. So just wait. I'll try to explain you. Yeah. Just see this. I will explain you the principal stresses in the Mohr circle. Let us consider a system. Let us consider a complex system where we have sigma x, sigma y, and tau xy are all acting. Okay, sigma x, sigma y, and tau xy are the shear stress tau. So this is called as a complex system. So please see how to draw the Mohr circle diagram. Let us first see how to draw the Mohr circle of So we have sigma x, we have sigma y, we have tau. These three values. అవునా కనిపించట్లేదా ఓకే వెయిట్ చేయండి 1 minute, there is some technical problem, I'll resolve it. I hope now the PPT is visible. Okay, so you asked about how to find out the principal stresses from the Mohr circle. So once you want me to explain once more, so I am trying to repeat what I have said yesterday. So let us continue. So how to find out the principal stresses by drawing the Mohr circle? So that is a question. So now what we have to do is, we have to construct a x-axis and y-axis, and the intersection of x-axis and y-axis we take as the origin. We take as the origin O. So from O, you choose some scale to represent the stresses. You choose some scale, say 10 newtons per mm square is equal to 1 centimeter. You choose such a scale. So if you choose such a scale, you know what is sigma x. So OA is equal to sigma x, sorry, OD is equal to sigma x. OD is equal to sigma x to the scale. So say for example, the sigma x value is 50 newtons per mm square. So put OD is equal to 5 centimeters. Put OD is equal to 5 centimeters. So D point on the x-axis is obtained now. Now on the x-axis, measure sigma y to the scale. Say sigma y is 20 Newton per mm square. So as per the scale, OB is equal to 2. So from O, measure 2 centimeters on x-axis, you get point B, point E, sorry, OE. OE is equal to 2 centimeters. OE is equal to 2 centimeters. So you get point E. So now we got point D and we got point E. A and B are not known to us still. We don't know what is point A and point B. So we know sigma x, we know sigma y. So we have put point D is equal, OD is equal to sigma x, point E such that OE is equal to sigma y. So we got point D and we got point E also. Now at D, you put a vertical line or line perpendicular to the x-axis such that the length of the line DF is equal to tau. The length of the line DF is equal to tau, the shear stress. Say for example, shear stress is 30 Newton per mm square. So as per the scale, DF will be is equal to 3 centimeters. So draw a perpendicular at D such that DF is equal to 3 centimeters. So now we got F point. Now we got the F point. Similarly at E, draw another perpendicular such that EG is equal to 3 centimeters. Such that EG is equal to tau. So to the scale it is 3 centimeters. So now we got G point. So now what we got now? We got a D point, we got E point, we got G point, we have got F point. Now join G and F. Okay. Now join G and F, which will cut the x-axis at C. Which will cut the x-axis at the center C. Okay. So now with C as center, CF or CG as radius, now draw a circle. Okay, now you draw a circle with C as center, CF and CG as radius, draw a circle. This circle will cut the x-axis at 2 points A and B. This circle cuts the x-axis at 2 points A and B. So OA is equal to major principal stress sigma 1 and OB is equal to minor principal stress sigma 2 or sigma 3, whatever you call. So OA and OB are the two principal stresses. So measure OA multiplied by 10, that is the scale, you will get principal stress in Newton per mm square. Similarly, measure OB and multiply with the 10, the scale, you get what is minor principal stress. Then you measure the angle FCD. You measure the angle FCD, that will give you 2 theta. Okay, that gives you 2 theta. Divided by 2, you get what is the location of the major principal plane. Location of the major principal plane. Okay. You add 45 degrees to theta, you get the location of the plane on which the shear stress is maximum. Theta plus 45. You add 90 to theta, theta plus 90, you get the location of the plane that is a minor principal plane. So this is how Nukaraju, sir, please explain again principal stress chapter. Please go through the video. You can replay the video any number of times. So that is the advantage of these classes. So you go through this video. Once more, you will understand the principal stress chapter. Sorry, can you explain about stress transformation? Stress transformation, I think it will come in the analysis. So in structure analysis, it will be dealt. Hemant Rao 22. Sir, you explained about the Mohr circle. Draw with diameter DE. Diameter DE, no. It is not with diameter DE, wrong. I have not told that. So what you have to do, this Mohr circle is to be drawn with C as center, CF or CG as radius. CF or CG as radius, draw a circle which will cut at points A and B on the x-axis. CA and CB is also radius, or AB is equal to diameter. AB is equal to diameter. DE is not diameter. DE is not diameter of the Mohr circle. So please see that the diameter of the Mohr circle is sigma 1 minus sigma 2. Okay, the diameter of the Mohr circle is sigma 1 minus sigma 2. It is not DE. DE, actually DE is sigma x minus sigma y. DE becomes sigma x minus sigma y. So actually, if you see this, this is CF is the radius. So CD is equal to sigma x minus sigma y by 2. Okay, CD is equal to sigma x minus sigma y by 2. So this is tau. The DF is the tau. So radius is CF, CG, CA or CB is the radius, which is equal to sigma 1 minus sigma 2. Radius is sigma 1 minus sigma 2 by 2, or it is equal to maximum shear stress. Maximum shear stress. Nukaraju. Sir, where we can download the PPTs? Again, it is in the JNTU website, so you please contact our administrators, our Director Academic Office for further information if you need anything. Pujita p442@gmail.com. Wheel loads are considered which forces? Then wheel loads are considered as point loads because the point of contact between the wheel load and the ground is almost very small. So the entire load is transferred at the point of contact between the wheel and the ground. So that's why they are considered as point loads or concentrated loads. Wheel loads are considered as point loads and concentrated loads. Pujita is asking the slope of, Gunashekar 1507 is asking the slope of stress strain curve in the elastic deformation region is equal to what? The slope of stress strain curve, what? You see, if it is linear stress and strain, linear stress by strain is nothing but Young's modulus. So the slope of the linear stress strain diagram gives you the Young's modulus. He is also asking uniform cross section, uniform E, uniform bending moment and uniform strength. Which is the property of the prismatic member? Nothing is property of the prismatic member. You have to define the property, what prismatic member you are choosing and what property you want, whether you want a uniform section or strength beam. So this, nothing of this is a property of the prismatic member. GRB Prakash 2000. Sir, what is the difference between conventional concrete and pre-stressed concrete? Okay, conventional concrete and pre-stressed concrete. Mr. GRB Prakash, I have explained to you that concrete is very strong in compression, whereas it is very weak in tension. So to resist tensile stresses, one method of reinforcement is by keeping steel reinforcement bars. That is what we call as reinforced cement concrete. The second method we use is pre-stressing the concrete. Pre-stressing the concrete. Okay. What we are going to do is we apply a huge amount of pre-stress even before the member is loaded with external loads. Even before the member is loaded by externally by the loads, by using what are called as steel tendons, we apply a huge amount of pre-stressing force on the concrete beam, okay, on the concrete member. So that is what we call as pre-stress. Before loading itself, we are applying stress. So that is called as pre-stress. Because of pre-stressing, we can make that there are no tensile stresses in the concrete member due to external loading. Due to pre-stressing, the pre-stressing force is capable of taking the tensile stresses, or we can adjust the pre-stress in such a way that there is no tensile stress in the member at all. So there is only compressive stress, so that there is no problem for the concrete beam to take the compressive stress. So such a system is called as pre-stressed concrete. Pre-stressed concrete. In the phase 2, there will be lectures on pre-stressed concrete. So I advise you to please go through those lectures on pre-stressed concrete. Pujita Yadav. In live cases, which one we take? The plane and where the maximum shear stress occurs on a plane. Pujita, we consider in structural design the plane on which maximum normal stress is there, the plane on which maximum shear stress is there. That also we'll consider. So depending upon the type of loading, depending upon the purpose for which the member is designed, we are considering either maximum normal stress or the maximum shear stress. All the criteria we have to consider. Akhil Akkineni, sir, your classes are so helpful in our preparation for GATE exam. Thanks for conducting online classes for GATE. And we did not get your material of today's class. Please go through the website. The material is uploaded. You can take. And thank you, Akhil Akkineni, for your appreciation of our class. Thank you very much. 124@gmail.com. Thank you, sir, to rectify the doubts. You are welcome, my dear friend. Ramisetti Ravindra, sir, you are explaining each and every topic in appreciation.ac.in. Pooja Kuntla, sir, your class is too good. You are bringing up confidence in us regarding this subject with your lectures and also your valuable sessions. Thank you, Ma. Thank you very much. I had a doubt. What is the difference between sigma T and a tau? Yeah, sigma T is the resultant shear stress or tangential stress. If in principal stresses only normal stress exists, why do we get tau in the formula of principal stress? Okay, I will clarify. You are just getting confused. I will clarify this point very clearly. So in the beginning, I too used to, when I used to study my engineering, I always have had this confusion. Pooja. So please understand, Pooja. Principal stress. First, I will explain you what is the sigma T and tau difference. Okay, it is a sign convention. Okay, whenever we say sigma T is the tangential. Sigma indicates stress. T is tangential. So sigma T is tangential stress because on an inclined plane, there is stress normal to the plane. That is we call as sigma n. There is plane tangential to the planes. That is called sigma T. Sigma n is the normal stress. Sigma T is the tangential stress. It is shear stress. A tangential stress is always shear stress. You can represent it as sigma and tau also. But for better understanding, I have given a notation that sigma n means normal stress. Sigma T means the tangential stress. You can put it as tau also. There is nothing wrong. Then your second doubt, I think you have to get clarified with this because you are getting confused. Sir, when principal plane there is no shear stress at all, then why should we calculate a tau, maximum shear stress? So please understand, principal plane is defined as a plane, but because of this major principal stress and minor principal stress, because of this sigma 1 and sigma 2, the major principal stress and the minor principal stress, on some other plane there will be shear stress. Some other planes will get maximum shear stress. It is not on the principal plane. Tau max is not on the principal plane. Tau max, the maximum shear stress is equal to sigma 1 minus sigma 2 by 2. This will occur on a plane at 45 degrees to the major principal plane. Please remember, it is not on the principal plane. So don't get confused. Be clear that on principal plane we have only principal stress. There is no shear stress. Principal stress is normal. But on a plane which is at 45 degrees to the major principal plane, we are having the maximum shear stress plane. So if you say this plane is major principal plane, at 45 degrees to this major principal plane, we have maximum shear stress. So don't get confused. On major principal plane, there is no shear stress, but the maximum shear stress plane is at 45 degrees to the major principal plane. So please, I hope this would have clarified your doubt. Don't get confused between these two. Okay. Pragna123@gmail.com. How can we find the number of principal planes and maximum shear planes in the given section, a rectangular circle? Number of principal planes, Ms. Pragna, if it is a three-dimensional body, we have three principal planes. If it is a two-dimensional body, we have two principal planes. So how to get the principal planes? Principal planes is equal to tan 2 theta. The location of the principal plane is tan 2 theta is equal to 2 times tau by sigma x minus sigma y. 2 times tau by sigma x minus sigma y. That's how you can get location of the principal plane. See here you can see in the Mohr, see this Mohr circle of diagram. What is CD here? CD is equal to sigma x minus sigma y by 2. What is this is shear stress tau. So from this figure, tan 2 theta is equal to tau by sigma x minus sigma y by 2, or otherwise tan 2 theta is equal to 2 tau by sigma x minus sigma y. Theta is equal to half of tan inverse 2 tau by sigma x minus sigma y. That gives you the location of the major principal plane. If you had 90 degrees, you get minor principal plane. So theta plus 90 gives the minor principal plane. Maximum shear stress is equal to sigma 1 minus sigma 2 by 2. The plane on which the maximum shear stress acts is at 45 degrees to the major principal plane. So at a theta plus 45. Hope this has clarified your doubt, Ms. Pragna. So now let us proceed to today's topic. So today's topic is theories of failure. So in civil engineering, the responsibility of the structural engineer is not only to design a structure. After construction and erection of the structure, by some reason, if the structure fails, we have to investigate the reason for failure also. We have to investigate the reason for failure also. So the investigation for failure can be of two types. One is an experimental method, the other one is from theoretical analysis. Theoretical analysis. So that is, there are two methods. One is experimental method or theories of failure. In addition to this, theories of failures can also be used in the structural design to avoid the failure. To avoid that type of failure, we can use theories of failure and have a factor of safety. In the design, we can provide a factor of safety using theories of failure. Okay, using theories of failure, we can provide a factor of safety also. Okay, so that's why these theories of failure are very important in structural engineering. There are different types of theories of failure. Okay, there are different types of theories of failure which we are going to discuss today. But in all the theories of failure, what we'll be going to do is compare between the complex loading system. Okay, compare the complex loading system and the yield stress at elastic limit. The yield stress in a simple tension test or simple compression test. Okay, see this point you have to be very clear. In all the theories of failure, we compare between two. We compare 2 points. One is the principal stresses and principal strains due to complex loading system. So the complex loading system already I have explained you. We have sigma x, we have sigma y, we have tau xy, we have tau yz, all that. The complex loading system. Okay, the complex loading system produces principal stresses, sigma 1, sigma 2, sigma 3, all that. Okay. So this complex loading system is one side, and the other side is the material which you are using for the member. So if you are using concrete member, say, so concrete. If you are using a steel girder, steel. So elastic limit, okay, elastic limit of the material, okay, strength at the elastic limit of the material, strength at the elastic limit of the material. These two we are going to compare. So if you have this point clearly in mind, this chapter is very simple. This theories of failure chapter is very simple. Only thing is you need to have this concept. In all the theories of failure, we will compare two objects, two things we compare. The first thing is the complex loading system represented by the principal stresses and principal strains. This is one. The second one is the material property, that is the strength at the elastic limit. The strength at the elastic limit, or the material property at the elastic limit. So how we conduct elastic limit test? We take the material, okay, we take the material, we apply a tension or compression, okay, we apply a tension and compression. So we go on measure the deformation, okay. By measuring the deformation, we get what are called as strains. So we draw the stress strain diagram up to elastic limit. We draw the stress strain diagram up to the elastic limit. So we get the strength at the elastic limit, or we also get what is strain at the elastic limit. We can get what is strain energy at the elastic limit. All this, okay. So please keep in mind, in this entire theories of failure chapter, you will be comparing two things. One is the complex loading system represented by the principal stresses and principal strains. The complex loading system represented by principal stresses and principal strains. And the second one is the material property at the elastic limit. Material property at the elastic limit. So whatever material you are using in the design, whether it may be a steel or it may be a concrete or maybe a aluminum or rolled steel joist, whatever material you are using, that material property at the elastic limit is a second point of comparison. So loading is on one side, principal stresses and principal strains because of the loading is on one side, and on the other side, the material property at the elastic limit is compared. So if you have this concept very clearly in mind, all the theories of failure you can easily attempt without remembering anything in the mind. Okay, without remembering anything in the mind, you can represent or you can solve all these theories of failure problems. If the material is subjected to either tensile stresses or compressive stresses, failure occurs when the stress in the material reaches the elastic limit. Okay, we are assuming that the failure reaches once the stress reaches the elastic limit. So this is the material property. Okay, if you take your first year classwork, when you apply the stress strain diagram for a mild steel rod, so elastic limit we consider is the limit up to which the stress is directly proportional to strain. Actually, if you go to real condition, the failure doesn't occur at the elastic limit. After the elastic limit also, we get yield point. Okay, we get yield point. At ultimate stress, then only the failure will occur. After ultimate stress only the failure will occur. But here we assume that the stress is directly proportional to strain, so which is within the elastic limit. So we are assuming that the failure occurs at the elastic limit. For any material, whether it is in compression or in tension, the failure occurs at the elastic limit only. That's what we are considering. In case of a material subjected to complex stresses, the stage of failure is determined either practically is not able to represent all the cases. That is why different theories have been proposed, and different theories are useful to tackle different types of problems. So that's why different theories of failures have come. So you don't think that one theory is applicable to all cases. So depending upon your problem, you have to choose which theory will represent the failure more accurately. So there are different theories of principal stresses. The problem is reduced to linking the three principal stresses to the stress at the elastic limit in case of simple. That's what I am saying. The entire problem of complex stress system, and number two is the strength of the material at the elastic limit. The strength of the material at the elastic limit. So these two will be linked, and the factor of safety will be determined in each theory of failure. The first one is called as maximum principal stress theory. Maximum principal stress theory. The second one is the maximum principal strain theory. The third one is called as maximum shear stress theory. The fourth one is called as maximum strain energy theory. The fifth one is called as maximum shear strain energy theory. So we have 5 theories of failures. So whatever this will be trying to link between the principal stresses due to complex loading to the strength at the elastic limit of the material. That two linking. Any theory you take, it will link these two. It will link these two. So if you take maximum principal stress theory, maximum principal stress sigma 1 is linked to maximum principal stress sigma 1 is linked to yield stress of the material in tension or compression. Okay, yield stress in tension or compression. The second theory is maximum principal strain theory. So in this case, the maximum principal strain is linked to the strain at the yield limit, the strain at the yield point of the material, the strain at the yield point. So strain theory, so strain is linked. Maximum shear stress theory, in maximum shear stress yield point. Okay, if the yield stress is sigma y, if the yield stress is sigma y, yesterday we have seen when there is only uniaxial stress sigma, when there is only uniaxial stress sigma, the maximum stress, shear stress is nothing but sigma by 2 acts at 45 degrees. Okay, acts at 45 degrees. So in maximum shear stress theory, the maximum shear stress due to principal stresses is compared to the maximum shear stress at yield point, which is nothing but if the specific, then sigma y by 2 is the maximum shear stress at the elastic limit in simple tension. So all these theories, a property will be compared with two things at the yield point. At the yield point. Because principal stress is normal to the plane, that's why it's also called as maximum normal stress theory. This theory is proposed by Rankine, so that's why sometimes it is also called as Rankine. Failure will occur when the maximum principal stress sigma 1 in the complex stress system reaches the value of maximum shear stress, maximum stress at the elastic limit in simple tension, or minimum principal stress reaches the elastic limit in simple compression. If you take tension, the maximum stress. If you take compression, the minor principal stress. So the comparison is between maximum principal stress or the major principal stress or the minor principal stress with a tensile yield stress, the tensile stress of the elastic limit, or compressive stress of the elastic limit. All the yield. Y is to represent the yield point. Okay, yield point. Y represents yield point. So sigma YT means the maximum tensile stress at the yield point in simple tension. Sigma YC is the maximum compressive stress at yield point in simple compression test. Compressive stress at the yield point of the material. So you can see now you can write in simple tension, if the major principal stress sigma 1 is equal to the major principal stress sigma 1 is equal to sigma yt. Sigma yt is the material property. Okay, sigma yt is the material property of the complex loading system. These two are compared. So if sigma 1 is greater than sigma yt, failure will take place. Sigma 1 is greater than sigma yt, failure will take place. If it is a compression, we compare with the modulus of sigma 3. Modulus, because sigma 3 may, compression you may put negative sign. That's why I am putting a modulus. So if it is minus 20, also you should consider 20. Okay, modulus. So modulus of sigma 3 is equal to sigma yc is the Rankin's theory, rank of safety. Sigma by sigma 1, we divide factor of safety. So generally for design purposes in working stress method, we don't use the yield stress. We don't use the yield stress sigma y. So we use a factor R occur. The failure will occur when the major principal stress in the complex stress system is equal to the tensile stress at the yield point, the tensile stress at the yield point in simple tension, or when the minor principal stress reaches the compression less than or equal to sigma yt for no failure. So factor of safety is equal to the material strength, the ultimate material strength divided by this sigma 1 value. So this Rankin's theory is valid for brittle materials. This Rankin's theory is valid for brittle materials such as cast iron. So for ductile materials like steel, this Rankin's theory doesn't give good results. So for brittle materials such as cast iron or a glass, Rankin's theory gives good results. Maximum principal stress theory is valid for thin-walled tubes. So similarly, if you are analyzing a thin-walled tube, maximum principal stress theory is generally used. The maximum principal stress theory is contradicted in the following cases. So failure in simple tension is caused by sliding at 45 degrees with the axis of the specimen. Thereby failure occurred due to maximum shear stress and not due to direct tensile stress. So when the failure is by sliding at 45 degrees, the failure is due to shear stress and is not due to direct major principal stress or direct tensile stress. So such a case as the principal stress theory is contradicted. Secondly, the material which is weak in simple compression can sustain large hydrostatic pressure than the elastic limit. So in such a cases, the principal stress theory is not valid and it is contradicted. So maximum principal strain theory. The second theory is the maximum principal strain. So now the principal strain will be compared to strain at the elastic limit. Okay, the principal strain will be compared with the strain at the elastic limit. Okay, so now see, this theory is Saint Venant's strain theory. It is also called as Saint Venant's strain theory or Saint Venant's theory. So what does this states? The failure of the material occurs when the major principal tensile strain reaches the strain at the elastic limit in simple tension. Reaches the strain at the elastic limit in simple tension. One part. The other part is when the minor principal to compression. Okay, when the minor principal strain reaches the strain at elastic limit in simple compression. Okay, so according to property, strain in direct tension at elastic limit. Okay, strain at elastic limit. So two things are compared. One is strain due to principal stresses. One is strain in elastic limit. So these two are compared. So there are two parts. One is tension part. The other one is compression part. The tension part is dealt with major principal stress sigma 1. The compression part is dealt by minor principal stress sigma 3. So according to this theory, failure occurs when major principal strain in tension is equal to strain at elastic limit in tension, or minor principal strain in compression is equal to strain at elastic limit in compression. Okay, strain at elastic limit in compression. So this Saint Venant's theory is more appropriate for ductile materials and for materials under hydrostatic pressure. So previous case we have seen it is not valid for hydrostatic pressure case. The principal stress theory was not valid for hydrostatic pressure case, whereas principal strain theory can be used for hydrostatic pressure cases and ductile materials also. For ductile materials also, it does not fit well with experimental results. Principal strain theory does not fit well with the experimental results. So now let us try to understand in terms of the formulae what is the maximum principal strain theory. So what is the principal strain in the direction of the major principal stress sigma 1? So there are sigma 1, sigma 2, sigma 3. Okay, 3 principal stresses. So what is strain in the direction of the major principal stress sigma 1? It is E1 is equal to sigma 1 by E, okay, minus mu times mu is Poisson's ratio. So because of sigma 1, in the direction of sigma 1, we get the strain is equal to sigma 1 by E minus mu times sigma 2 by E plus sigma 3. Similarly, the principal strain in the direction of minor principal stress sigma 3. So E3 if we want, E3 and E3. Now, what is the comparison now? E1 is compared with the tensile strain at elastic limit. How do you get the tensile strain at elastic limit? If sigma yt is the tensile stress, that divided by Young's modulus will give you the tensile strain. Because it is a uniaxial stress, it is subjected to only sigma yt. So sigma yt by E is equal to strain. So compare these two. Now 1 by E, E1 should be greater than sigma for failure not to occur. E1 should be less than or equal to sigma yt by E, or otherwise 1 by E into sigma 1 minus mu times sigma 2 plus sigma 3 is equal to sigma yt by E, or otherwise sigma 1 minus mu into E3, the principal strain, the minor principal strain, equal to sigma yc by E. Okay, sigma yc is the compression in direct compression. So should be equal to sigma yc. That is the major principal strain theory. Major principal strain theory. So you need not remember this formula. Don't remember anything. You just use the concept. The principal strain theory, what it says, the failure we take minor principal stress. That's all. From that you get this formula. So use the concept. No need of remembering any of this formula. So to prevent failure, the left hand side must be less than the strength of the material. So sigma 1 minus mu times sigma 2 plus sigma 3 should be less than sigma yt, or in compression sigma 3 minus mu times sigma 1 plus sigma 2 should be less than sigma yc, that is the stress in compression, the yield stress in compression. So see what is the difference now. In major principal stress theory, sigma 1 is less than sigma yt. Sigma 3 is less than sigma yc. Now the formula is modified. Sigma 1 minus mu times sigma 2 plus sigma 3 is less than sigma yt, or sigma 3 minus mu times sigma 1 plus sigma 2 is yc with factor of safety. We divide sigma yt and sigma yc with factor of safety. Sigma t and sigma c are allowable stresses, or safe stresses, or working stresses. So sigma 3 minus mu times sigma 1 plus sigma 2 should be equal to permissible stress in tension. Sigma 3 minus mu into sigma 1 plus sigma 2 is equal to permissible stress in compression. So this is the yield stresses. If we divide them by factor of safety, we get the maximum shear stress theory. The maximum shear stress theory. This theory is proposed by Coulomb's or Tresca's. This is also called as Coulomb's or Tresca's theory. Mostly it is popularly known as Tresca's shear stress theory. So again same concept. Shear due to principal stresses. Okay, shear stress due to, here the maximum shear stress theory, we compare shear stress due to principal stresses with shear stress at the yield point or the elastic limits that of the material. Okay, so this theory states that the material will fail when the maximum shear stress tau max in the complex system reaches the value of maximum shear stress in simple tension at the elastic limit. Maximum shear stress at the simple tension at the elastic limit. So one side maximum shear stress due to principal stresses. On the other side, shear stress, maximum shear stress in simple tension, okay, at the elastic limit. So if you take sigma yt is the stress at the elastic limit, okay, sigma yt is the tensile stress at the elastic limit, sigma yt is the tensile stress at the elastic limit. In uniaxial, the maximum shear stress due to sigma yt will be equal to sigma yt by 2 because there is no stress in the other direction. In uniaxial stress, we get the shear stress is half of the normal stress. So the maximum shear stress is sigma yt by 2. You can see it is sigma yt by 2. Whereas the maximum shear stress due to principal stresses is sigma 1 minus sigma 3 by 2. So major principal stress, minor principal stress, half of that. So what is the criteria? Sigma 1 minus sigma 3 by 2 must be equal to sigma yt by 2. Or otherwise sigma 1 minus sigma 3 is equal to sigma yt. So if you, this is for failure criteria. This is failure criteria. Sigma 1 minus sigma 3 is equal to sigma yt is the failure criteria. Okay. If F is the factor of safety, the working stress sigma t is equal to sigma yt by factor of safety. So for no failure to occur in the structural design, we take sigma 1 minus sigma 3 should be these problems, these theories. So the maximum shear stress theory or Tresca's theory gives good correlation with experimental results on ductile material. If you are designing a shaft to carry the power supply, okay, to carry the power supply, then you can use the Tresca's theory. The theory does not give accurate results for the state of shear of pure shear. It is not giving good results for pure shear cases. There is no sigma x, there is no sigma y, there is only shear. There is only tau acting all the way. So such cases, this theory is not giving good results. This theory is not applicable in case where the state of stress consists of triaxial tensiles. All are tensile stresses. Sigma x, sigma y, sigma z are all tensile stresses. Tensile stress system. So for a triaxial tensile system, this theory is not applicable. So now we'll go to maximum strain energy theory. Okay, the maximum strain energy theory. So again, this is proposed by Beltrami-Haig. Okay. So in this maximum strain energy, now what we are going to link, what we are going to compare, the strain energy due to principal stresses on one side, the strain energy at elastic limit due to sigma yt. Okay, the strain energy at elastic limit due to sigma y or sigma yt, whatever you call. Okay. So now what is the statement of this theory? According to maximum strain energy theory, the failure of the material will occur when the total strain energy in the material reaches the total strain energy of the material at the elastic limit in simple tension. That's what we have to compare strain energy at the elastic limit in simple tension with strain energy due to complex loading system and principal stresses. Okay, so this is what we have to take. So if you take a three-dimensional stress system, the strain energy per unit volume, the strain energy, generally we compare strain energy per unit volume because on both sides volume is there. So we will come. Okay, what is the strain energy due to sigma 1, sigma 2, sigma 3 per unit volume? It is called as U. Okay, U is equal to 1 by 2E into sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. So this is the strain energy due. Then what is the strain energy per unit volume in axial tension? It is sigma yt square by 2E. What is sigma yt square by 2E? That's all. Here sigma by 2E. sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu into sigma 1 sigma 2 sigma 2 sigma 3 plus sigma 3 sigma 1. This should be equal to sigma y square by 2e for failure. For failure, okay. For no failure to occur, the left hand side should be less than the right hand side. Okay. So if you cancel 2e on both sides, this is the equation. This is the governing equation. Sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu into sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1 must be equal to sigma y square. This is the governing equation for failure to take place in maximum strain energy theory. So now if you are considering a two-dimensional stress system, there will square plus sigma 3 square minus 2 mu sigma 1 sigma 3 is equal to sigma y square. So put sigma 2 is equal to 0. That's all. So for this is for the failure. For the design, the working stress is equal to sigma. So if you take working stress is sigma, for design sigma square, where sigma is the working stress or the safe stress. This theory is applicable for ductile materials, particularly in case of pressure vessels. So if you are solving a pressure vessel problem, so then this theory, strain energy theory, is very much applicable. The theory does not applicable for materials. Sigma y theory will not be valid for materials, which for materials also the results are not comparing with the experimental results. The theoretical results are not comparing with the experimental results. So now we'll go to last theory, which is so before going to last theory, I explained one popular problem which is generally asked in strain energy theory. In strain energy theory, a case of hydrostatic pressure is in the below the water. Okay, all phases, in all three phases, it is subjected to same water pressure WH. The maximum compressive stress will be, find out the maximum compressive stress. So yield stress of the material, let us say yield stress of the material 2 is equal to sigma 3, 2 mu sigma by E is equal to sigma by E into 1 minus 2 mu. Okay. So 2, 3 sigma square by E answer. So this is equal to sigma sorry, sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu sigma 1 sigma 2, same answer. Or it is proposed by von Mises Henke. This theory was proposed by von Mises Henke. Okay. So here also the concept is same. Now we have shear to what is shear strain energy at elastic limit in simple tension. At elastic limit in simple tension. So these both things will compare. That is the theory. This is proposed by von Mises. So this theory states that the elastic failure in a material occurs when the shear strain region of shear strain energy at elastic is having yield stress is same in compression and tension. Sigma yc and sigma yt both. This theory is very much valid. Now let us derive the governing equation for this material. First let us take the complex stress system represented by sigma 1, sigma 2 and sigma 3. In a 3 dimension we have 3 sigma 3. So the shear strain energy per unit volume, the shear strain energy per unit volume is equal to 1 plus mu by 3e, 1 plus mu by 3e into sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 sigma. This can also be written, this formula can also be written like this. Shear strain energy is equal to 1 plus modulus, so 1 plus mu by 6e into sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. Or otherwise in terms of shear modulus, this can be written as 1 by 12g into sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. So this is the strain energy due to sigma 1, sigma 2, sigma 3. Now what is the strain energy due to strain energy due to yield stress? The strain energy due to yield stress is equal to sigma yt square, 1 by 6g into sigma yt square. So equate these two. Okay, equate these two. You get the governing equation. Sigma 1, this is the equation on the one side, that is due to principal stresses, and this is due to yield. Only thing you have to have in mind is if you are applying, or otherwise if it is normal strain energy, it is sigma yt square by 2e. Normal strain energy is equal to sigma yt square by 2e. A two-dimensional stress system, sigma 2 is equal to 0. So you can, if you apply sigma 2 is equal to 0 in this equation, you get sigma 1 square plus sigma 3 square minus sigma 1 sigma 3 is equal to sigma t square, sigma yt square. That is the, if you want figuring the structure, then if you design sigma, if sigma t is equal to sigma yt by f, the factor of safety, for design purposes, sigma 1 square plus sigma 3 square minus sigma 1 sigma strain energy theory. So we have defined 5 theories. In all the 5 theories, it is very simple if you understand that two things will be compared. On one side, the complex stress system represented by sigma 1, sigma 2, sigma 3. On the other side, in simple, sigma 1 should be equal to the yield stress design. Sigma 1 should be equal to sigma yt by factor of safety, working stress. That's all. If you are considering sigma 2 by E minus mu times sigma 3 by E, that is a strain in sigma 1 direction, this should be equal to strain at the elastic limit, sigma yt by E. Stress at the elastic limit is sigma yt, Young's modulus is E. What is strain in simple tension? Stress by Young's modulus. So, what is the maximum shear stress due to principal stresses? It is either sigma 1 minus sigma 3 by 2. Okay, minor principal stress, minor principal stress. So, find out the difference between principal stresses, half it, which is the maximum value, take that, that is the 2. That is the governing equation. Done. Similarly, in strain energy theory, what is the, we are doing sigma 1, sigma 2, sigma 3, 3 principal stresses are there. We have what is the strain energy per unit volume. Okay, we compare the strain energy for unit volume. Okay, so remember even this also, you can write U is equal to 1 by 2 into sigma 1 E1 plus into sigma 2 E2 plus 1 by 2 sigma 3 E3. That's all. That way strain energy you will get. You can remember this or you can directly get from the concept. So this is the strain energy governing equation. That's it. So in case of shear strain energy, what we are comparing, shear strain energy 12G into sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 1 by 12G into sigma 1 minus sigma 2 whole square. The strain energy is sigma yt square by 6G. So equate these two, sigma yt square by 6G. Equate these two, you get sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square must be equal to 2 into. It's very simple. It is very simple. There is nothing difficulty. And whatever we have discussed, the design criteria I have given here. So for maximum principal shear stress theory, sigma 1 minus sigma 2, sigma 1 square plus sigma 2 square minus sigma 1 minus sigma 2 should be less than or equal to sigma y square. So this is the design criteria which we have discussed in today's class. So there is no need to remember any formulae. Whatever concepts we have discussed, with these concepts you can find out and solve 60 megapascals and 140 megapascals. So he has given us sigma 1 and he has given sigma 2. One is major principal stress and one is minor principal stress. Simple. Sigma 2 square plus sigma 3 square minus 2 mu response. The homogeneous state of stress for a metal part undergoing the plastic deformation is, he has given the state of stress. That stress tensor he has given 0, 0, minus 10. So this is the stress tensor. Where the stresses. So the state of stress is equal to this. So sigma is equal to 5 megapascal. From yesterday's class, sigma 1 plus sigma x plus sigma y by 2 plus or minus half of the root of sigma x whole square plus 4 tau xy square. So substitute what is the value of sigma x, sigma y and tau xy. We get what is the sigma half of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square should be equal to sigma yt. So simply substitute this, you are going to get what is sigma yt. Okay, what is sigma yt? So shear stress is equal to sigma y. We want to use maximum shear stress theory. Okay, he has given sigma x, he has given sigma y, he has given tau xy. Okay, shear strength of the material sigma x minus sigma y whole square plus 4 tau square. So from this we get shear stress is 50 megapascals. Okay, shear stress is 50 megapascals. That's it. It is very direct question. The shear yield stress is 1 by root 3 times the direct stress. Sigma 1 is equal to 60, sigma 2 is equal to 5, and sigma 3 is equal to minus 40. For the material of the component, the tensile yield strength is sigma y yield stress is 200 megapascal. According to the maximum shear stress theory, that's what is asking. So now we have to compare maximum shear stress due to principal stresses with the shear stress of, okay, it is 100 megapascals. Now from our knowledge, sigma 1 the max intention is 220, sigma xy is equal to sigma yx is equal to 80. So it's actually tau xy. This is printing mistake. Tau xy is equal to tau yx is equal to 80, and all other stress components are 0. The yield strength of the material is 468 megapascals. The factor of safety on the basis of maximum shear stress theory is simple. He has given us sigma x, he has given us sigma y, he has given, we may get sigma 1 by 2 as the maximum shear stress. So that criteria if you consider, you get tau max, so the maximum sigma 1 by 2 is 260 by 2 is 130 also. Okay, 130. So this is 130. So from this also 468 divided by 130. 468 divided by 130. Major principal strain to tensile strain sigma y by E, or minor principal strain to sigma yc by E. Right? In shear, sigma 1 minus sigma 2 by 2, the third theory, sigma 1 minus sigma 2 by 2 equal to sigma y by 2. Okay? In strain energy theory, if you go, the strain energy due to sigma 1, sigma 2, sigma 3, that is U for unit volume, is compared with sigma y square by 2e, that is the strain energy at yield point or the elastic limit, sigma 6g, sigma y square by 6g. That's all. That is the yield, that is the shear strain energy at elastic limit. So both compare these two. That's all. Not the governing equation. So with this simple concept, also for investigating the failure and also to come up with the computation of the factor of safety. So for all these purposes, we can use problems. We can use these 5 theories of failure. Each theory of failure is applicable to certain materials, which also I have discussed. So go through these concepts and cracking in the gate examination. But as far as possible, I request you to, so tomorrow we are going to deal with the torsion chapter. So I advise all the students to join back tomorrow afternoon at 3 p.m. to discuss about torsion. Torsion of really. Have a nice time. Bye bye. See you tomorrow.